Thank you for being with us today. Nice seeing you all on site and online. We're looking forward today to hear Professor Edoardo Charbon. Edoardo is full professor and the head of the Advanced Quantum Architecture Lab here at EPFL. His talk today is entitled Photon Counting Cameras for Quantum Imaging Applications. His talk will last for approximately 45 minutes. We have then time for questions at the end. Edoardo agreed to take urgent questions online. Otherwise, please feel free to put them in the chat and we'll try to take them up at the end of the talk. Before diving into the presentation, I'd like to thank Edoardo for his availability and the entire CIS team for making the event happen again today. Edoardo, if you want to yours.
Thank you very much, Jan, for this kind introduction. And again, you can interrupt me anytime for urgent questions or maybe not so urgent questions. I think it's going to be a discussion among friends. So today I'm going to be talking about photon counting, and I would like to start from these people that actually made it happen. And this is my lab and a new member of the lab, Doka, called Yuki, which means snow in Japanese. And of course, I would like to thank the Swiss National Science Foundation, the European Commission, as well as Canon and a few others. Just a few words about photon counting. I'd like to show you some examples. This is a light in flight experiment that we did some time ago with Kazuo Morimoto, is now back at Canon. So what we did here is we took an image on camera known as Megapixel. I will talk about this camera later on. And we basically stopped the light propagating from a laser into various mirrors that you can see that it follows a certain path. So you can immediately see a relativistic effect, which is given by the fact that the light is actually moving at a faster, what appears to be faster than light, than the speed of light, when coming towards you, and at the slower speed when it comes away from you. This is actually a very simple explanation for this. Light always moves at the speed of light, of course, but due to the fact that we are using light to manifest this propagation, then of course light will have to propagate a longer distance when it moves away from the camera than when it moves towards the camera. That's why you have this effect. Another interesting effect that you can see here is light propagating in a fiber, and you can see during the propagation it actually changes color. And this is also a well-known effect of dispersion in single and multimode fibers. This is a more practical application for which single photons could be used, and that's a so-called augmented reality, where you basically give a value to or extra information to the elements that you see here. And what you need in order to achieve this kind of augmented reality is, in premise, distance and the depth of the scene that allows you to see where the various actors in the scene are. This is perhaps something more familiar, where this was taken with a LiDAR, I believe from Velodyne, that allows you to reconstruct the image in 3D at very high speed. And this is necessary, especially for self-driving and also for safe driving, in order to reconstruct in 3D an image in order to determine if there is a potential danger, or if a pedestrian, for example, is in front of you and risks his or her life from you coming and not seeing him or her. So, of course, there are a lot of different applications. We talked about automotive safety, but there's also night vision, autonomous driving, as well as gaming and industrial applications that require this kind of detectors. So how do we perform photon counting? There are many ways of performing photon counting, and today I'm going to be focused on one that I know very well. It's been actually researched for some time, and I think EPFL is the forefront since 2003 It's called SPAD, or single photon avalanche diode, that essentially has become a low-cost device since people started implementing it in CMOS. CMOS is economy of scales, and therefore it makes a lot of sense to go and to become CMOS compatible. Of course, let me just give you a quick review on photodiodes. Photodiodes are usually operating in a diode in reverse bias, so about here, where the optical gain is 1. But if you're operating in this regime, which is close to the avalanche voltage, then you're going to get an intrinsic gain that can go from 2 to 10,000. But of course, you can see here that the gain is highly unstable. So the solution to this problem is to go one step further and to operate the device above breakdown. And so in this case, basically the gain is infinite irrespective of the bias. Well, more or less irrespective of the bias. So this is what you can build. You can build a diode that has in series a resistance known as a ballast resistance. And effectively what you do, you are ready to receive a photon when you're operating this voltage at above breakdown. So it's a voltage VB plus VE, so excess bias voltage plus breakdown voltage. A photon arrives, the photon gets absorbed, it generates an electron-hole pairs, it gets accelerated by the very large electric field. By creating a current through the device, you're actually going to go through RQ, which is the ballast resistance, which is then in turn going to increase this voltage and quench the avalanche. And there you go, you have a pulse that is in correspondence to the photon. Now, this particular pulse can be positive or negative, but the important thing is that it can be converted into digital pulse by just using a comparator. So that's a very simple device that basically is the interface between photons and electronics. Electronics from that moment on can be exclusively digital. So the interesting thing is the fact that the timing resolution, so the capability of detecting photons with a very high precision, has been recently shown to be of the order of 7.5 picoseconds. The photon detection probability, the sensitivity of this device, can be as high as 50 to 60%, whereas the fill factor can be as low as 40% and as high as 80%. The dead time is the time that it takes for the device to actually be ready for the next detection. And this can be as low as 1.5 nanoseconds. So that means that in principle, you'll be able to detect gigaphotons per second on every detector independently. Of course, the price to pay is a certain dark count rate, which is usually in the order of counts per second. CPS stands for counts per second, sometimes even going to kilocounts per second. And then, of course, after pulsing, is another non-ideality effect, which means that you can have multiple pulses in correspondence to a single photon. So these are very recent results obtained with detectors that are relatively large as 100 micrometers, with the electronics that, thanks to the fact that these detectors are completely CMOS compatible, can be completely integrated near the detectors. And actually, it is completely invisible here because it's extremely small compared to the detector. So with this technique, you're able to achieve a after pulsing probability of the order of 0.1% and 0.1%, and recently a resolution of the order of 7.5%, 7.5 picoseconds. The dark counts are again in the order of single CPS in the large detector, and the sensitivity can be as high as 55, almost 60%. So here you can see a sensitivity that varies as a function of the excess bias voltage, but also as a function of wavelength. And of course, here you can see that indeed with this type of device, you can reach sensitivities of the order of 10% at 800 nanometers, at 5% at 900 nanometers, which are the wavelengths in the near infrared that are used in LiDAR, in most LiDAR applications. This is a response that you can see on the detector that shows that the jitter indeed, even though the detector is relatively large, can achieve a minimum of 12 or even recently a 7.5 picosecond. SPTR stands for single photon temporal resolution. So fine, but what can you do with it? These are some of the examples of detectors that we built over time, from the very early one that demonstrated here in 2004 the capability of being completely CMOS compatible, to the very recent one in 2020 during the pandemic that demonstrated the very first megapixel maiden SPAD. So you can see a variety of applications here, going from intrinsic single photon synchronous detection to detectors for PET, and even detectors for optical joysticks. So here you see a couple of detectors, this one and this one, that actually were the basis for the ST microelectronics product that you can find in almost every cellular phone, including mine, that measures the distance between the cellular phone and the user, and thereby reducing the power consumption. Okay, so but how do we actually achieve large format SPADs? Well, the first thing that you need to do, of course, is to scale down the detector, a single pixel. And this has some limitations. So, for example, if you're using a technology relatively advanced, now not so advanced anymore, but of 40 nanometers, you can get essentially 9.2 micrometer pitch, which is relatively large compared to what you can get in conventional detectors. But why is that? You can see it from the ITRS tech nodes versus the pitch achieved in conventional CMOS image sensors, that is going in 2020 below the single micrometers pitch, whereas in SPADs, this is actually 1 order of magnitude higher. And the reason for that is mostly the fact that there are quite high voltage requirements, there are guard rings that protect the premature edge breakdown here. And also for many years, SPADs were considered of no economic interest until very recently. So a solution to improve this situation, of course, is to use backside illumination and 3D stacking. And this actually came only recently to SPADs. So this is an example of how low you can make the pixels. And I think the world record at the moment is about 2 micrometers. And with this type of detector, you can, in principle, achieve megapixel detectors in megapixel sensors in that are very, very small, millimeter by millimeter square. So, of course, you can also shrink it down further using pitch, using guard ring sharing, and using even more advanced technologies. 55 nanometers an example, but we have even further reduced, we have even further reduction with more advanced technologies. But the true holy grail is really to go 3D completely. So in conventional CMOS image sensors, people have gone in 3D for some time. So this is an example of backside illuminated or PSI image sensor, where essentially you're taking the detector, you flip bond it onto another wafer, and usually in more advanced technology. And then after the hybrid bonding, you perform a thinning in such a way that light can actually go through without particular impediments. You can also do the same with front-side illuminated detectors, as you've seen earlier, where in this case you need a true silicon via that will that is essentially a metallized hole that goes through the detector itself and connects it to the back to the next chip. So the idea here is to have only with the detection on one side and all the processing, including quenching and recharge, on the other side. And why is that? Well, because we want to do a couple of things. First, we want to use maybe a combination of different technologies, one that is optimized, for example, in infrared, and one that is optimized for speed. And at the same time, we want to introduce much more implementation, much more functionality on the backside of the chip. So maybe you can even think or dream of further development where you're going to have an intermediate layer of processing, then a memory layer, and then a communication layer. The sky's the limit. And why is that? Because the true bottleneck of photon counting on a chip is really data communication. So here is an example of a chip that we published in 2018, where you see a relatively small array, 252 by 144 SPADs, that has all the electronics that is needed for latch chains and TDCs, or time to digital conversion, for the time of arrival calculation. And all this silicon outside is actually used for compression and IOs. So you'd say, well, if this could be implemented in a lower technology, in a much more advanced technology, it would be very nice, but it's not enough. You really have to go in 3D in order to get much more functionality at your disposal. So let me just go over one of the latest detectors that we had the chance to build, and that is MegaX. That was actually the first megapixel photon counting camera in the world. So the reason why we built this detector is because we wanted to implement a LiDAR, or time of flight direct detection, direct time of flight detector. So the way the direct time of flight works is as follows. You have a source, usually a laser, that sends a photon bunch, and then you have an object here, and the distance is measured as c times the time of the round trip divided by 2. So the theory is easy, but the implementation is not so easy, especially if you have 1 million detectors that cannot implement the TTC on each detector. So what we've done is that we've constructed a gate-based device where basically we divide the time into sections, and any type of refraction is actually going to be detected and is going to be used to reconstruct the response of the detector in terms of the histogram. So this way you can detect, you can calculate the reflection, and from that you can calculate the position of the target. But the nice thing with this approach is that you can also see multiple reflections, and therefore you can construct, for example, images through glasses or through semi-transparent objects to see really the three-dimensional reconstruction all along. So this is a photomicrograph of the chip that comprises a megapixel SPAD with a pitch of 9.4 micrometers. The gating, the size of the gate is 3.8 nanoseconds, and the number of frames per second, the number of frames that I can get in a second, is of the order of 24,000. Of course, this will generate a very large data rate of 24 gigabit per second, but everything is implemented in in about 1 centimeter squared. So this is a photomicrograph of the pixels. We've done 2 types of pixels. I will not go too much into the details. I will just explain one of the pixels. That again is based on our detector, the quenching transistor that is replacing the larger resistors, the inverter, and then actually the utilization of 2 transistors that perform the gate very, very precisely. So it is possible to activate and deactivate the detector in a matter of picoseconds. Then, of course, you need the memory, which is implemented with a dynamic memory, in this case, a simple capacitor. And this is the actual implementation of the detector. You can see a few more transistors and a relatively simple implementation of the timing diagram. This is the characterization of the chip, and you can immediately see the dark count rate that is actually quite small, the order of 1 count per second, and then sensitivity in the order of 25%, and as well as a power consumption that is quite well contained within limits. This was very important because you have 1 million detectors working simultaneously. So if you want to build an image like that, and this is an image that demonstrates the resolution of 1 micrometer, is of 1 million, sorry, 1 million, yes, 1 micrometer indeed. It can be achieved through a very coarse implementation of the camera. So this is my alma mater, OSCE, that is in a photograph together with some elements. You can see the very high resolution of the image that you can see here. And actually, the nice thing is that in this image, you see that there's absolutely no processing whatsoever. So this is exactly what comes out of the camera. This is a departure from conventional cameras where DSP is actually quite large, and there's quite a bit of DSP that is required. And then, of course, you can use your gate, and the gate, as you can see here, that is actually quite uniform, with about deviations of the order of 150 picoseconds. And this is a 3D image that is constructed using the gate. So in other words, you're scanning the gate onto the picture, and you reconstruct the depth. So you can see here different colors corresponding to the depth of the device, of the scene. And here is the actual distance versus measured distance up to 1.6 meters with a error of the order of a centimeter or so, actually even down to a few millimeters. Okay, so we've seen that you can make cameras that they can be relatively large, but what do you do with it besides 3D images? So I'd like to give you an overview of some of the applications for which this photon counting can be used. So one of them, and actually here I have a non-exhaustive list of quantum imaging type that you can see. So starting from ghost imaging, quantum distillation, quantum LiDAR, and non-line of sight LiDAR, which is something that I will explain in detail. But there are other types of imaging that we define as quantum imaging, such as quantum state tomography, quantum holography, super resolution using quantum techniques, quantum plenoptic cameras, and even Quanta Burst Photography. In the interest of time, I will not cover this, but I'd be happy to answer any questions that you may have. I have a lot of backup slides in case you have questions about this type of imaging. So let's start from ghost imaging. In order to understand ghost imaging, you have to start from classical imaging first. So you have the imaging plane and the object plane. So from the object plane, of course, this is the lens that projects onto the imaging plane in a way that we are also very used to, according to this formula that relates the focal length to the distances between the object in the object plane and the imaging plane. Now, the question is, all right, that's all fine. This is something we understand. But what if instead of using a source that is made of conventional photons, I introduce a concept of entangled photons? So that's where the quantum effect comes. So entangled photons, in order to understand entangled photons, you need to understand the concept of entanglement. And if you look at Wikipedia, you'll find that physical phenomena that occurs when a pair or group of particles is generated, interact, or share spatial proximity in a way such that the quantum state of each particle or the pair or group cannot be described independently. It's really the essence of entanglement. So in other words, when entangled, optical photons may have correlation that actually involve not only polarization, but also time coincidence and geometrical relative positioning. So in other words, you can use pairs of photons that independently interact with the scene, but that are actually interacting with each other as well. And therefore, they cannot be described independently. So if you go back to our initial image, what we can do is the following. We can essentially eliminate one of the lens and use a so-called SPDC, So that is basically spontaneous down conversion, which is the crystal that generates entangled photons. The idea is that I generate two photons going on opposite directions. One will hit the object plane. The other will hit the image plane. On the image plane, I will construct an array of detectors that I then correlate with a single detector on the object plane. So in this way, I basically can eliminate all lenses, reconstruct the original classical approach, but do it only by using coincidence between detectors. So I no longer need a complete camera on one side, but I just need coincidence between objects. Okay, why do you want to do this? Because in this way, I can basically separate completely any type of interference coming from light that I don't care about, that I want to eliminate, from the light that I actually care about. So in other words, I can separate background from the light that I intend to image. I can also do the same way if I take the two entangled photons and I shoot them in the same direction onto an object. So in this particular case, I can use a beta barium borate BBO crystal. I generate pairs of photons. And then what I will see is that the two photons will have a dependency that is time-based and spatial-based as well. So in other words, they're central symmetric with respect to the center of the lens, but they also arrive at the same time. So what does it mean? It means that if I take a sequence of images at very high speed, I will be able to detect whether a photon is a single photon or a double photon, but not entangled, or if I have both entangled photons on the single plane. So in this case, for example, I have nothing here, even though I have temporal resolution, but here I have temporal resolution and spatial resolution, and therefore I can recognize the entangled photons, which means that essentially I can shoot a very small number of photons onto an object that is flooded with a very large number of photons that have nothing to do with my photons. I can hide that information and I can later extract it. Okay, if I cannot distinguish, I have a very fast camera, I will not be able to distinguish the idler and the signal from all the other photons. But if I can have a camera that is super fast and possibly single photon detection capability enabled, then I will be able to do that. And why would I want to do that? Well, for example, one thing I would want to do is hide information in plain sight. So this is an example where I have the target object that is generated and that is imaged using a laser and a BPO, and another object that is actually present on the other side. So if I just look at conventional camera, I will see this image. So I will not be able to distinguish the two objects. If on the contrary, I will be able to distinguish only entangled photons, then in this case, I would be able to extract the correct image. So this is a technique that is known as quantum distillation, because I can distill out an image that is visible in plain sight and completely separated from classical images. So this is very important. If you imagine that the classical image could be the background light and the background illumination, and the image in the quantum image is the image that you're interested in imaging. So which brings me to the next big application, which is known as quantum LiDAR. So now I can combine the vision, the 3D vision that I introduced to you earlier, and I can simply say, okay, fine. Now I can see in depth, but I can also erase everything that is actually not related to the image I want to see. And this is extremely important because if I want to, for example, see images in 3D that are in plain sight under the light illumination, I want to use a super small power laser, like a laser pen, for example, only 1 milliwatt. Because in that case, I will imagine that the classical image is the background and the quantum image is the object of interest. And I can extract an object of interest even though it may be completely flooded in light. So this is important if I want to remove completely the effects of background illumination from LiDAR. So this is an experiment that we demonstrated in a recent paper that appeared on Optics Express just a month ago. The idea was to essentially generate a bunch of entangled photons and then direct them towards a beam splitter, and then basically the SPAD camera, and use a laser, two lasers, one for generating classical images and one for generating quantum images. So here you can see that by just performing very fast detection and using the gating that I demonstrated to you earlier, I could distinguish the two images. So this is another view of the implementation of the quantum LiDAR, where again, you can in real time reconstruct images that are classical versus images that are quantum. Another application for which this quantum LiDAR approach could be very useful is the so-called non-line of sight. So suppose that you want to find objects that are behind a wall, and all you have at your disposal is a source that is reflected onto various walls. So you want to reconstruct complex reflections and multiple reflections over walls in such a way that you can predict what is behind the corner. Why is that important? Because LiDAR is only looking ahead. But for example, if you want to capture a child coming from behind the corner at high speed, and you cannot predict it because he or she will come just in front of you, and you have absolutely no way to see, in this technique, you will be able to predict and to see that person coming towards you ahead of time, and therefore brake. So this is one of the applications, but there are other applications that are perhaps related to safety and security. For example, if you are looking at smoke in a smoky environment, you're looking at objects and people that you want to save, and you want to be able to see through this complex scenes. So this is a demonstration that was done by a colleague of mine, Daniele Faccio, and here you can see the reconstruction of the image by just looking at these multiple reflections. It's a complex problem with a complex solution. He uses the machine learning to actually come up with a proper reconstruction. But the reconstruction is actually very accurate. So all you have to do is understand the geometry of the problem that you're trying to solve, and then essentially solving an optimization problem, which you can do with training more efficient and more effectively. So this is another thing that you can do, is reconstruct humans they are, but also trying to figure out who they are. And in this way, you can actually, again, use machine learning, implementing multiple reflection and realizing the positions of the object. So here you can see, for example, the reconstruction that was done, and the matrix that shows the recognition of the person, not only its position, but also not only their position, but also the person that was responsible for the reflection. Okay, so I'd like to show you a next generation view of detector, MindHive, which is the first SPAD camera that with embedded neural networks. So in this camera, we built an array of SPADs, and the SPADs, I remind you, are natively digital devices that are sending the pulses of the detection, just like neurons in our brain, in our eyes, and send it onto a network, digital neural network that is actually representing that is implementing complex recognition activities. So this is the entire detector. You can see the SPAD arrays here, the channels and the neural networks at the bottom. with even an SPI for programming them, just to give them a little bit of flexibility. In addition, of course, we have TTCs, or time to digital converters, that also determine the time of flight in case of 3D integrated 3D detection. So you can, with this detector, essentially detect not only the depth of objects, but also combine it and perform classification using the neural networks embedded. So this is the actual implementation here. And then you can see the various parts, including the neural network that was achieved. And with this, we actually implemented a neuron using 9 types of nonlinear responses. And we were able to reconstruct signs, handwritten signs. The next generation is a more elaborated recurrent neural network, which is based on the so-called gated recurring units. And here you can see how the unit is actually implemented. The input goes onto the detector itself, and the output goes into a memory that reconstructs the position. So in other words, what we are trying to do here is reconstruct the position in 3D, not by creating a histogram like we were doing before, and then reconstructing the position of the object, but reconstructing the position of the object directly by looking at the various measurements. The advantage of doing that is 1, you gain in memory, 2, you gain in power, and 3, you're much more robust because you can actually see in very complex scenes. So this is a result that we achieved with this technique using a 40 hidden size. And so here you can see the ground truth and the estimated distance up to 7 meters. And ultimately, we're looking at much larger distances now. This is another example of imaging acquisition. So we did the training with synthesized images, and then we reconstructed it using real images. So in this case, we use a laser of 780 nanometers. The IRF was in the order of 200 picoseconds, so not terribly good. And there was an illumination, and the laser was only 2 milliwatts, and we could see up to 30 meters. We have also demonstrated at 6 milliwatts in the outside up to 300 meters, just to give you the flexibility that the system allows. So this looks a little bit bulky. So you have various optical components, and here but it's actually, believe it or not, portable. And so here the reconstruction. So this was the reconstruction in distance after training, and this is the images that we achieved: the 2D image and the 3D image. As you can see here, you can see even a 1 millimeter support for this figurine that was actually reconstructed at the right distance. And here you can see the distances that in the color-coded agenda. Okay, so I'd like to conclude maybe with a couple of take-home information. So one of them is that all along in my lab, we've been following Moore's law. We use Moore's law to our advantage, and we use the economy of scale to reduce both power, noise, and to increase the size and the pitch. So therefore, being able to increase the size of the detectors. We reached 1 megapixel, but I think the road is still long, and we can even think of larger detectors in the future. With the introduction of 3D ICs, this has further accelerated this direction, this trend. And I believe that this is actually going to go even further. But this is also going to give us very interesting opportunities, because not only we can use SPADs, which clearly have emerged as a technology of choice for fast detection and potentially quantum imaging applications, but also thanks to the 3D stacking, we will have to have a multiple impact, to multiply the impact of these detectors, not only by introducing parallelism, but especially by introducing the type of machine learning algorithms that I've shown in my talk. And finally, we think that photon counting and embedded artificial neural networks, not only they're ideally suited for quantum imaging, but they are here just to be expanded in the future, whereby clearly a massive increase of functionality is going to be enabled by more and more advanced technologies, such as 16 nanometers, then after that 10, and after that 7 nanometer technologies. And with this, again, I'd like to invite you, in case you're interested in, not in La Diablerie this year, but virtually in the International SPAD workshop, which is a workshop that I created in 2018, and that is going to be growing. I think if we had to take a picture of the people participating in the workshop, we wouldn't be able to fit them in this space. And with this, I'd like to thank you very much for your attention, and I'd like to answer any questions you may have. Thank you.
Last chance, maybe.
No, I think it's time.
It's done, or maybe let me say some words of closing the seminar. First of all, many thanks, Edoardo, for your talk.
Thank you. It's my pleasure.
Thanks to all of you on site and online for having been with us. Just a small announcement. So this Wednesday, we're looking forward to hear Professor Khan at the next Thicken AIP seminar series. And on 2nd of May, we're looking forward to welcome Professor Huge at the next Get to Know Your Neighbor seminar. And now, everyone here, please grab a snack and stay a couple of minutes longer. And everyone online, I hope to see you soon again for one of our next seminars. Goodbye.
Goodbye.